We would like to present a highly maneuverable flying squirrel drone with controllable foldable wings. The ability to perform high maneuverable operations directly affects important functions such as collision avoidance and trajectory tracking. The drone's maneuverability becomes more important when it avoids sudden obstacles or people, or encounters obstacles that are difficult to detect from a long distance, such as windows. The conventional drones has limited thrust of each motors, making it difficult to immediately perform high maneuverable operations such as direction change and sudden stop at high speed. To respond well to situations such as emergency stop, additional repulsive force should be generated. Flying squirrels use various flight strategies using air resistance by patagium. Inspired by flying squirrels, we developed a drone with a structure that can overcome the physical limitations of existing drones by utilizing air resistance with foldable wings. In this study, we would like to find out how much foldable wing helps to follow the trajectory, which is including the dramatic speed change section. The flying squirrel drone consists of a carbon pipe and 3D printing parts. The fuselage consists of 3 floors, with the lowest part consisting of a crank mechanism, a power distribution and ESC system at the middle end, and a main board and a communication device at the upper end. 2 servo motors control the movement of the left and right wings. 1 servo is connected to 2 RRRR linkage mechanisms, the orange link structure and the red link structure shown in the image. Each link structure moves the connected RRRP mechanism so that the wings can be spread and folded. This linkage structure allowed us to adjust the range of motion of the sliders within limited hardware conditions. The silicon membrane wings are divided into 3 parts: left wing, right wing, and rear wing. The silicon membrane wing was made of Ecoflex 0020, and a 0.3 mm wing film was made using a mold made of 3D printing. The created wing membrane has a hole, which is inserted into each joint of the crank structure to fix the wing. Since the wing membrane was not attached to the link and was fixed only on the joint, it was possible to eliminate the phenomenon of tearing due to large deformation of silicon when folded and unfolded. The 4 rotors on the flying squirrel drone were controlled by a nonlinear controller called the integral backstepping controller. The roll pitch yaw of the drone was controlled through this controller. Since the physical properties of the wings are not solid, it is virtually impossible to completely calculate the air resistance, so the wings are controlled through reinforcement learning methodology. In order to control the wings, rewards were configured to accelerate faster in the section where the drone should accelerate and decelerate faster in the section where it should decelerate. However, if the learning proceeds as it is, it converges to a suboptimal that changes the area slightly without completely folding the wings. The orange graph illustrates this well. In order to create a clean folding and unfolding motion of the wings, we conducted learning using human demonstrated data. After conducting an experiment in which the experimenter judged and folded and unfolded the wings with a switch, learning was conducted so that reinforcement learning could follow the characteristics of the obtained data. Human demonstrated data is clean without noise when folding and unfolding wings, but the timing is not optimal. It is a purple graph of the image on the right. Finally, the learned result maximizes air resistance by reliably spreading the wings at the optimal timing, and in situations where resistance is not required, the wings are firmly folded to minimize air resistance. The experiment is done as follows. Using the Bézier curve, create a trajectory that satisfies the above conditions, and let the integral backstepping controller follow the trajectory. At the same time, the wing controller adjusts the wing area to reduce the error of the trajectory tracking. As a result of the experiment, pure integral backstepping control without wing control alone showed low reference tracking performance. Looking at the red graph of the left image, it can be seen that there is a big difference from the reference in the rapid deceleration section. The result of applying the wing controller can be found in the right image. The faster the speed section, the greater the difference in deceleration performance depending on the presence or absence of the wing controller. Motion capture was used for measurement, and the size of the motion capture experiment field was small, so it could be tested only in a low-speed section. Nevertheless, results showed consistent performance differences. Thank you for your attention.